let's recall the application we started last time on C6 free graphs, but we're looking at incidence graphs, so points and lines in the plane. So we have this theorem we want to prove. Recall, Samarity-Trotter proved that for any n by n vertex incidence graph of points and lines in R2 in the plane, let's call it G, then the number of edges is big O of n to the 4th thirds. This bound is tight. There is a construction. So remark, is this the matching lower bound? Construction n to the 4th thirds. Since this is not the focus now, I will not mention this construction. The theorem we want to prove is by Shoimoshi. We know the incidence graph of points and lines is C4 free because two lines, their common points is the most 1. Shoimoshi proved that if you have C6 free condition, so you have incidence graph of points, lines in R2, C6 free condition will imply that, so this graph again G is little o of n to the 4th thirds. And we can improve the upper bound a little bit. And as I said last time, it is conjectured, still open, that under the same condition, one can do better, polynomially better. So this is not known. The idea is we're going to use, because this graph has come from geometric setting, the edges are not uniformly distributed. There's some clustering happening, some edges that bump together into a dense patch. And how we're going to capture this dense patch is by Matuszak's cutting lemma. So the proof consists of 2 parts. In the first part, we're going to use, so the idea maybe let me use blue. The idea is first to use Matuszak's cutting lemma to capture a dense asymmetric bipartite subgraph. And then on this asymmetric bipartite subgraph, we're going to define cleverly auxiliary graph and apply removal lemma. And then removal lemma. All right. So let's recall. Let's see the details. I put the Matuszak's lemma here. Wait. So this is Matuszak's lemma. Let's recall. It says that for every n points in the plane, and you choose some parameter r, which will be, roughly speaking, the number of parts we want to partition P, the set of points, into. So we can partition it into roughly r parts, where each part is roughly n over r size, up to a factor of 2. So constant doesn't really matter. Such that, so where's the clustering of edges? In this case, the clustering is reflected by the fact that every line that we take after we have this partition, every line can only go through points in roughly square root r many parts. Remember, the total number of parts is r, and square root r is a lower order term. So the neighbors of every vertex in this incidence graph is clustered into very few parts. Okay, so the idea would be, let me expand this idea a little bit. Basically, suppose, maybe we should just directly write the proof. So here's the cutting lemma. Let's see the proof. Suppose this is not true. We're going to derive a contradiction. Suppose we have incidence graph of n points and n lines in the plane, and the number of edges of it is of order of magnitude n to the 4/3. Suppose G is m point. Okay. Let me just assume G is given as a m by m vertex incidence graph. Suppose that E of G, do I use explicit number? I did. So let me use this number. Suppose it's linear in n to the 4/3, not little o. Okay. Now what we're going to do, we let's take a parameter beta, which is much smaller than c, and we want to set r, this parameter r, and which is the number roughly up to a constant factor of 2, the number of parts we want to cut P into. So we set r to be beta n to the 2/3. We will cut it into n to the 2/3 part. Each part of size roughly n to the 1/3. Okay. Now apply Matuszak's cutting. We will get this partition. P equal to, let me just write it like as d1 to dt, where t is roughly r. Good. And the property we have is every vertex, which is a line on the right, has neighbors only in some absolute constant c times square root r many parts, many different di's. Now we're going to do, okay, so we have the partitioning. We now want to do is to zoom into a part that captures lots of edges. This is just done by pigeonhole. But before we do the pigeonhole, we're going to do some clever cleaning. So what we're going to do is the following. We say that for every line here on the right, what we know is since it has neighbors in this many parts. Now we look at each part where it has neighbor. If its degree is at most 2, then we're going to delete these edges. If it's more than 2, we keep all of them. All right. This is a preparation. Later we can use removal lemma. So for every line, and for every region di, which is one of these parts on the left, if the degree of this in DI is at most 2. Then we delete edges from L to DI. We do so for every line and every region DI. Let's first see how many edges we deleted. We will see that this is negligible amount. The total number of edges deleted during this cleaning process is at most, let's see, we have n vertices on the right, we have n lines, times each region we delete, if we delete edges, if it has too few neighbors, we delete at most 2. If it's at least 3, we don't delete it. So it's at most 2 for each region. And the number of regions where it has neighbors is big O of square root R. Okay, so it's times 2 times big O of square root R. What is square root R? We know R is here, beta n to the 2/3. So this is big O of beta to the 1/2, if you do the calculation, n to the 4/3. 4/3, that's correct. What's this compared to our number of edges? It's basically beta compared to C. But since we take beta much smaller than C, we know that this is negligible amount. So let's say this is at most half of the edges of our graph. So we still retain half of the edges after this cleaning. Good. Now, what do? Now what we do is every vertex now either has no neighbors to a part, like this, no neighbors, or if it ever has edges, it should send at least 3 neighbors. It has to send at least 3 edges, right? We simply use pigeonhole to zoom into one DI that receive above average number of edges between left and right after the cleaning. So by pigeonhole, there exists I in T, where T is roughly R, such that the number of let's do the calculation, the number of edges between DI and L is at least, we have this many edges survived, half of the EG, and the number of parts is T, right? But T is at most R, so T is at most R, so this is at least EG over 2R. EG is C n to the 4/3. R is this guy, so you do the calculation. This equals to, what is it? C over 2 beta, right? Yes. C over 2 beta times n to the 2/3. This many edges. One thing to keep in mind is that as we choose beta to be much smaller than C, this leading constant tends to infinity. It's a huge constant. Okay. Good. Now, now we focus on this L and DI at this moment. Let's define the set L prime, which is a subset of L. What do we know? We know the vertices here from the right after the cleaning to DI either sends at least 3 edges, or it has no neighbors. Because if you send at most 2 to Ti, we delete it already. So let L prime to be the set of vertices in L that has at least positive degree. So let L prime be vertices having degree at least 3, degree having positive degree, hence at least 3 because of the cleaning. To Di. Okay. Very good. What do I want to do now? Now I'm going to define my auxiliary graph. So how do I define auxiliary graph? We define auxiliary graph. Let's call it gamma. Let's say it has vertex set E, V, and E, where the vertex set of gamma is Di. Let me use red to draw this graph. Auxiliary graph has its vertices on Di. What are the edge sets? Well, it's very simple. We look at every vertex in L. In its neighborhood, we know it's at least 3 sides. We're going to put down vertex disjoint triangles. That's it. If it's divisible by 3, let's say degree 6, we put 2. If it's not divisible by 6, let's say degree 8, right? We put down 2 vertex disjoint triangle and just leave the other 2 vertices isolated. Don't do anything to it. Or just writing words for each L in L prime. Put down DL in DI divided by 3, take the floor, meaning vertex disjoint triangles in its neighborhood in DI. Okay. Now, and we call such a graph, we call such a triangle an L triangle. If it sits, it's the triangle coming from gamma we built from this collection. We call it L triangle. Okay. Good. Now what do we do? First, observe that the collection of L triangles is edge disjoint. So here, for example, this one, from this vertex, you can think of the vertices in L prime as having colors. Then this red vertex has degree 3, we put on 1 triangle. If you have a vertex has degree 6, let's say, or 7, then I put down 1, 2, and there's a vertex. I just leave it isolated like this. So the collection, observation, all L triangles are edge disjoint pairwise. Okay. Why is that so? What does it mean you have 2 triangles sharing an edge? That would mean this triangle is in the neighborhood of a vertex, and this triangle is in the neighborhood of a different vertex. So you have two vertices on the right sharing two vertices on the left as neighbors, which is a C4. But remember, incidence graphs of points and lines in the plane has no C4. That's the proof, okay? As G is C4 free. Okay. We are sort of in the shape of applying removal lemma in the contrapositive form. Remember, removal lemma in the contrapositive form is saying when you have, if let's say this order is m, if you have quadratic in the order of the graph, meaning edge disjoint triangles, then you in fact has you have positive density of triangles. This is how we want to apply it. So let's first get some estimate on the order of the graph and the number of triangles in this collection so that we can have the numbers correct to apply removal lemma. First, let's see the order of the graph, di. So the order of the graph, gamma, which is on the vertex at di, has size. It's up to a factor of 2. Remember, the size is between n over r and 2n over r, right? So up to a factor, constant factor of 2, let me be lazy and write it like this, is n over r size. And r is what? I choose it to be beta n to the 2/3. So it's 1 over beta n to the 1/3. Roughly of order of magnitude n to the 1/3. Good. So this is the order, which let me call it M. Now I want to say that the number of edge disjoint triangles is roughly M squared. Then we can show that the total number of triangle is in fact M cubed by triangle removal lemma. So let's see how many L triangles which are edge disjoint in gamma. The number of L triangles is basically you sum up this quantity over all vertices in L prime. Okay, it's roughly the number of edges between di and L divided by 3, roughly. But what's the number of edges between di and L prime? It's the same as number of edges between di and L because we only delete vertices that has no degree to get from L prime, to get from L to L prime. So the number of edges of order of magnitude n to the 2/3 divided by 3 is still n to the 2/3 after constant factor. And the order of the graph is n to the 1/3. So we are in the correct range. The number of edge disjoint triangles in the graph is quadratic of the order of the graph. Let me write down this. So the number of edge disjoint triangles in gamma is at least the number of L triangles, which is equals to sum over L in L prime dl in di divided by 3, take the floor. Because as d over 3 floor is bigger than d over 6 for any d at least 3, we know d, this degree is at least 3 after cleaning. So this is easy to prove. We have, this is at least sum of, let me get rid of the floor sign, L in L prime, 1 over 6 dl di. Okay. But what is this? This is the number of edges between di and L prime. Wait a second. To be precise, let me call this graph G prime after the cleaning. So what I really mean is in G prime after the cleaning, we still have this many edges, all right? Yes. So this then equals to 1 over 6 EG prime DI and L prime, which is the same as EG prime DI and L. And what is this quantity? Here. So we have C over 12 beta n to the 2/3 edge disjoint triangles. So this is big omega of m squared. M is order of gamma. So what do we know? By removal lemma, by triangle removal lemma, we get that the number of triangles in gamma is actually positive density. So it's big omega of m cubed. That's what we conclude. All right, so we want to derive final contradiction. How do we want to derive final contradiction? We want to say that give me a second. We want to say that this total number of triangles is more than the number of L triangles in gamma. Remember, what is L triangle? L triangle are the triangles that we put down in the neighborhood of a vertex when we're forming gamma. If you have a triangle in gamma, which is not one of these that we put down, write down to get gamma, what does it mean? That means every edge of this triangle in gamma comes from different vertex on the right. This will imply what? It looks something like this. You will get a 6 cycle. 1, 2, 3, 4, 5, 6 in your graph. That's a contradiction. Our graph is C6-free. So this is what we want to do. Let me see how I write it. So let me again have this picture here. So we have L prime, we have DI. Okay. Let me see. Actually, using a result, we can give an upper bound on the size of L prime, and then give an upper bound on the edges between DI and L prime, and then which can give an upper bound on these, the number of L triangles. But I think now there's a simpler way of doing this. Let me think. So all we need to do now is to show this number of triangles is more than the edge destroying number of copy of triangles in gamma on DI. So I think the simplest way to do this is on the vertex set of size m, the maximum number of edge destroying triangles you can get is of order of magnitude m squared. Simply because if you edge disjoint, right? I think we did this before. It's a Steiner, the best you can do is Steiner triple system. Edge disjoint, so you can only have triangles like these. You cannot have triangles like these. Okay, right. We did this before. And the number of edge disjoint triangles in gamma is at most big O of m squared. I think the best is perfect Steiner triple system, which is roughly m squared over 6. So let me just put big O. We don't need to be that precise. And what is m? M is a function of n, and n tends to infinity. So we can assume m is sufficiently large. When it's sufficiently large, m cubed is definitely bigger than m squared, despite this constant in the front, which is much less than m cubed. This implies there exists a triangle in gamma that is not an L triangle. So what does it mean? You have this triangle that look like this, where this edge is coming from some purple points. This edge is coming from some black one, and this one is coming from some blue one, okay? Lo and behold, you look at here now in our graph. 1, 2, 3, 4, 5, 6. You have a 6th cycle in the graph G, which is a contradiction. This implies C6 in G, contradiction. Any question? I remember now, this is very easy to prove. The number of edge disjoint triangles. You look at this collection, for every pair, you have m choose 2 pairs. The number of triangles containing these pairs is at most 1, because triangles are edge disjoint, right? So the number of edge disjoint triangles is at most m choose 2. Okay. Any question? Good. If there's no question, let's move on to the next application of regularity lemma. This is again a very classical application on enumeration type of problems, on counting problems in extremal combinatorics. So the next application, regularity lemma as containers. Okay. Let's see what order I want to explain this. Okay, let me first explain the problem. Then it will make sense of how I explain this container thing. So the problem is very simple problem. We're saying in Turan's theorem, recall, it's a very natural enumeration problem. Let's now recall Turan's theorem saying for every n vertex graph G, which is K, let's say R plus 1 free, then the number of edges E of G is at most the number of edges in this n vertex R-partite two-round graph. Complete R-partite balanced complete R-partite graph, which is roughly 1 minus 1 over R n square over 2 plus minus some constant. Okay, I think something like this. This constant depends on R. Okay, now we want to know, the problem we consider now is counting the number of KR plus 1 free graphs on a fixed set of vertices. So we should count labeled graphs. Now, consider labeled graphs on vertex set n, which is the first n integer. You can see all the graphs on the first n integers. And we want to count those that are KR plus 1 free. How many of them are KR plus 1 free? A natural question. There's a simple lower bound. What's the simple lower bound? Anyone? Let's say R is 5, so you know you have your partition set of vertices into n over R size roughly, plus minus 1, and KR plus 1 free means you have R parts. You put all edges in between, right? This is your two-round graph. What's the lower bound? You need to come up with the construction of many, many KR plus 1 free graphs labeled on the set of vertices 1 to n. What's a simple way of doing this? If a graph is KR free plus 1 free, then any of its subgraph is also, of course, KR plus 1 free. That means we can just take, let's say, this two-round graph and take all possible of its subgraph. The number of subgraph is 2 to the number of edges of this graph. For every edge, we have two choices. Take this edge in our graph or not take this edge in our graph. So, by taking all possible subgraph of some labeled of some TNR on the first n integers, we will get the lower bound, this number, KR from free graphs on n is at least 2 to the 1 minus 1 over R n squared over 2, right? Plus minus some constants. Number of edges in here, I'll put it here. So we have a lower bound, this lower bound. Now the question is, how tight is this lower bound? This is what we want to prove using regularity lemma. We want to show that this is fairly tight. You cannot improve this constant at all. So we want to show, this is a theorem by Erdős, Kleitman, and Rothschild. In the 70s or 80s, I don't quite remember. 80s maybe, we check the year, that the number of KR plus 1 free graphs on the first n integer, so labeled, equals to 2 to the 1 minus 1 over r plus minus little o1 n squared over 2. So up to some little o n squared error in the exponent, this constant is tight. All right, we already have the lower bound here. All we need to do is to use regularity lemma as containers to prove that the number of KR free graphs is at most. So what we need to show, for every epsilon bigger than 0, there exists n naught depending on epsilon, such that for every n bigger than n naught, the number of KR plus 1 free graphs on n is at most 2 to the 1 minus 1 over r plus epsilon n squared over 2. Okay? This is what we want to prove. Good. Any question? We need to show this. All right, how do we show this? The idea is in this word, containers, what it means is that as n tends to infinity, it's not practical to count KR plus 1 free graphs one by one labeled, right? We want to somehow group them into bundles, into groups, different groups. And we hope that the number of groups we group them into are not so many. We will see later that we will group them into constant many groups, such that in each group, all these labeled KR plus 1 free graphs is almost contained into one graph, which itself is triangle free, KR plus 1 free. For any KR plus 1 free, all the number of its subgraphs is at most this many, right? Just by taking all its subgraph, because its size is no more than this due to KR plus 1 freeness. So then we can count all of them by looking at their supergraph, taking all possible subgraph, this many, times the total number of these supergraphs, which is constant many groups. And that's the idea. So let me write down. So how do I write it? So, right, let's do it this way. We want to count this thing, right? The KR plus 1 free graphs labeled on the first n vertices. So let's take one such graph and see what we can get out of this. So consider a KR plus 1 free graph, labeled graph on the first n integers. Let's call it G. Now what we're going to do is apply regularity lemma. Apply regularity lemma on G. What do we get? We get some reduced graph. Okay. What do we also get? So this is the reduced graph. Let's say it looks like this. Just for example, okay. We also get some graph that corresponds to We also get this, remember, this graph GR, which is subgraph of G, and the number of edges of GR is the number of edges of G minus little o n squared. So you delete few edges not corresponding to R in G. It looks something like this. This is GR. Okay. First thing to observe is that the reduced graph R must be KR plus 1 free. So the first thing is R is KR plus 1 free. This is just by counting lemma. By counting lemma, R is KR plus 1 free, the reduced graph. Because if the reduced graph has a KR plus 1, then the original graph has many KR plus 1, which is a contradiction. Good. Now we're going to do the following. Instead of this time looking at GR, we're going to blow up the reduced graph R. We know that each part is M size, right? Where M is roughly N over R. R is the number of vertices in reduced graph. Remember, R is a constant number. Depends on this epsilon, which is and little m. Oh, I use little m as a lower bound of the number of parts, so I should use a different symbol. Let me use capital M, shall we? Okay. So R is a constant. What I'm going to do now is I want to blow up this reduced graph. Very simple. Each part is of size n. And whenever there's an edge in the reduced graph, I put complete bipartite graph. Okay, so this is the graph. I will write it as R bracket n, which is the n blow up of R. Okay, now we're going to observe something crucial. What do we want to observe? I want to ask how many edges of G. First thing to notice, let's do it slowly. GR, first thing to notice, is a subgraph of this graph, Rn. This is almost trivial. Why? Well, GR is those correspond to R. The edges in G between clusters that's linked by an edge in R. And R, the blow up of R is exactly the same thing, but I put all edges between clusters. So of course, this is a subgraph of that. No problem. And what does that mean? That means this R, the blow up of R is like a container containing almost all of G. So almost the whole graph G is contained inside this container. Okay, let me write it down. So this means almost the whole G is contained in this container Rn as a subgraph. Does it make sense? Okay. In other words, I'm using this property that the part that we clean from G to get GR is little o of n squared. So in other words, i.e., EG minus ERN, the edges in G, but not in the blow-up of R, is a little o of n squared. Almost the whole G is contained in R. Okay. Good. This, now I can write down the statement, which is what I mean, regularity lemma as a container. So what's the statement? Let's first see what we have done so far. What we have shown is that for any KR plus 1 free graphs labeled G, there is some reduced graph, which we obtain from applying regularity lemma. There is some graph R, which is this reduced graph, of bounded order, the number of vertices bounded, such that its blow up almost contain G. Okay? For every KR plus 1 free graphs, we can find such blow up of a bounded size graph that almost contain G. That's true for every such G. So that means if you want to count all KR plus 1 free graph G, you just need to take those containers. And the number of these containers, Rm, blow up, is the same as the number of choice of R. What's the number of choice of R? It has R vertices, which is bounded. So the number of choices of R is also bounded. Let's write it. What we have shown is that any KR plus 1 free graph on N is almost contained in the blow-up of some bounded size graph, bounded order graph, which is the reduced graph R. Okay, so the number of choices for this bounded size graph R is at most what? If you even think of R as labeled, this is like R factorial. You permute the vertices of R as ordered, and then you have R vertices, right? So the total number of edges is R choose 2. Then you just choose all possible graphs on R choose 2 edges. You take for each edge between 2 vertices in R, you either choose it or not choose it. This many choices. So number of choice of R is constant. This is constant, depends only on epsilon and m. And m usually we choose it as a function of epsilon. So this really is just a function of epsilon, bounded size. Now let's write this into a theorem, which is the tool we use to prove Erdős, Kleiman, and Rothschild. So theorem, regularity lemma as container. It says that well, let's be precise. So let me not be precise. Precise one, you should write for every epsilon there exists n naught, such depends on epsilon, such that the following is true for n bigger than n naught of epsilon. And now I will just write in terms of little o n, little o notation. It should be, let's say how we write it. Yes, so I will write, there exists a family C of graphs let me call it containers. There exists a family of there exists a family C of container graphs on the first n integers labeled, satisfying the following with the following property. First property, the number of graphs, the number of containers in C is constant number. The only constant number of containers. Second property, each container, let's call C in C as a graph on N, it's triangle free. Look, this is the container, right? Which is a blow up of a reduced graph, but the reduced graph is also KR plus 1 free, right? Not triangle free, KR plus 1 free. Each container is KR plus 1 free. Third thing, this is the conclusion here. Every KR plus 1 free graph labeled is almost contained in one of these containers. For any KR plus 1 free graph, let's call it G, on the first n vertices, I can find the container C in C such that G is almost containing C, such that the number of edges in G are not in C is little o of n squared. So this means G almost subgraph of G, C, some C, right? Good, this is the lemma. Now we can prove Erdős, Kleiman, and Rothschild. The proof is very simple, given this container from regularity lemma. Proof of Erdős, Kleiman, and Rothschild. So what do we need to prove? Let's recall. The number of KR plus 1 free graphs on N is 2 to the 1 minus 1 over R plus little o1 times n squared over 2. So we want to count such graphs. Let's take a container, family of containers C, as in the previous theorem. Okay, take this family of containers. I have to keep referring to this. Good. Let's move here. Okay. Take the containers. Now, let's think of how we can construct the number of ways. Think of how do we count the number of KR plus 1 free graphs? Number of KR plus 1 free graphs on N. You just think of how to construct them. Such a graph. Okay? We can construct in this way. Step 1, choose a container, C in C. The number of choices is the size of the container, which is constant. Step 2, after you choose the container, you then choose a subgraph of the container to edges. You choose some edges of the container to be included in G. Okay. How to construct such a graph G? Okay. Choose an EG intersect EC, basically. Choose how many edges in C we want to include in G. And number of choices for this step is at most 2 to the number of edges in C. Okay, but what do we know? C, by the second property, is KR plus 1 free, n vertices. C is KR plus 1 free, the container, implies that EC is at most, by Turan's theorem, n squared over 2, 1 minus 1 over r, plus little o 1. So this implies this is at most 2 to the 1 minus 1 over r plus little o 1 n squared over 2. That's the second step. Third step. Good. We choose the edges in C that's to be included in G. Now we need to choose the edges out of C that belong to G. There's so many, right? Choose EG minus EC. And this is by the second point, we have these. This is by the third point here. We have the number of such choices is at most, how many? Well, we have n choose 2 total number of edges on the first n integers. All possible pairs, n choose 2. Among these n choose 2, we have to choose a little o n squared to be this guy. Little o n squared. So easy to compute. This is 2 to the little o n squared. And that will give us all possible KR plus 1 free graphs in N because of this theorem. Because we know every KR plus 1 free graphs on N is almost contained inside some KR plus 1 free container, and number of containers bounded size. Okay, so multiply all these number of choices together on each step, we get an upper bound on this. If you multiply them together, constant, main term, lower order term, all together, we get this number as desired. Desired bound. Okay, any question? One remark I want to make here is that maybe some of you might say, okay, so here, each container is KR plus 1 free, that's nice. But this almost containment, if you don't like almost containment, if you want to eliminate the fact that G has edges outside of C, you just want to make it complete containment, that's possible. Okay. All you need to do is you have this blow up of N. These are the graphs in your container, right? Then you just sprinkle on this, each one of these things, you sprinkle at most this many edges to recover all possible choice of these exceptional edges. All right, you can get complete containment. Let me write it. So alternative 1' is that you will have So 2 prime is the same as 2. Each container, no, 2 prime is different also, sorry. What I want to say is in 3 prime, what we're going to do is we'll require for every kr plus 1 free graph G on N, we require exist a container. You have a complete containment such that G is a subgraph of C. Okay? If you require this, you need to sprinkle this many edges on each container in C. And that will result in the number of containers, instead of constant, you need to multiply 2 to the little o n squared, right? Which is coming from n choose 2, choose little o n squared edges. The total number of ways to sprinkle these edges. So this will become 2 to the little o of n squared. And how you should change the second point, since the edges you sprinkle is little o n squared, even though the resulting graph now is not kr plus 1 free, this container, but it's almost kr plus 1 free. HC in C is almost kr plus 1 free, i.e., the number of kr plus 1 in C is little o of n to the r plus 1. The kr plus 1 density is 0. This is a different version, 2 prime. Both versions are, you can derive this EKR from both versions, all right? Now, I want to move on to the last application of regularity lemma. So, the last application is linear size clique in special family. I should say clique density forbidden induced forbidden subgraph and induced forbidden subgraph. Okay, so the theorem I want to, the application I want to see is this theorem by Gelfash, Hubenko, and Shoimoshi. And I want to also mention extension by Holmsen. Okay, so the original statement I write in black is for every n-vertex graph G with the property that your edge density is positive. So let me write K2 of G, this edge density how do I write? The number of edge density. Okay, let me use this symbol for now. K2 of G, this is edge density. Okay, let me just write here. When we write KT of G, this is KT density. which is the number of KTs in G normalized by n choose T. The total maximum number of KT is n choose T. So you normalize it by this factor, you get the density of KT, which is the fraction of T tuples that induce a copy of KT in G. So if your edge density is positive, and your graph is induced K2 2 blow up free. What is this? K2 2 blow up. That means you replace a vertex by an independent set of size 2, and between them you put an edge. So this is basically induced C4 free. Okay, and the conclusion is the largest clique, the clique number of the graph is linear in n. This is somewhat surprising because if you don't have this condition, the forbidden induced subgraph condition, if you only have positive edge density, you could have a complete bipartite graph where the edge density is 1/2. But the clique number is 2. You don't even have triangle, right? But with this induced forbidden subgraph condition, we suddenly get the largest possible size of a clique, which is of order of magnitude linear in the order of the graph. Okay. And the extension by Holmsen, he proved actually even something even more general. But let me just state, he proved it extended to even the hypergraph version. But let's just state the graph version, which says, if you require KT density of G to be positive, but now instead of induced K2 2 blow up of K2 free, you have induced K2 blow up of KT free. So let me draw the T equal to 3 case. You have 3 group of vertices of size 2. Inside each group of size 2, there's no edge. So there's no edge, no edge, no edge. But between different groups, you have all possible edges. You don't have this graph as an induced subgraph. And your KT density is positive, you will get the same conclusion. All right? Let's first prove the simpler version, T equal to 2 version, the black one. So if your number of edges is Cn squared and induce C4 free, you have this. How do we prove it? I'll just do a sketch of the proof. T equal to 2. Okay, i.e. number of edges of G is n squared, and you induce C4 free. You want to prove there exists a clique linear in n size. How do we prove it? So we okay. Apply regularity lemma. On G, we get reduced graph R, right? We get not reduced graph. I don't care about reduced graph. Okay, yeah, why not? We get a reduced graph R. What do we know about this reduced graph? Because our graph is dense, it has positive edge density, the reduced graph must contain at least one edge in the reduced graph. Okay, which means as E of G is little o of n squared, this implies there exists a pair V I V J, which is regular and dense. Regular and dense. Now we're going to look at this regular and dense pair. Let me call it A and B actually to be easier. Instead of VI, VJ. So is this the regular, a pair AB that's regular and dense. So this is our AB. Each is of size linear in N, remember? Each cluster of the partition is linear in N. Regular and dense. We're gonna divide it into two cases to consider. The first case is a simpler case. Case one is the density of, let's say, one of them, A. The density of A, edge density, what does it mean? That means the number of edges in A divided by A choose 2. This density is bigger than 1/2. Let me just say 2/3. Okay? If this is bigger than 1/2, then we can actually find there exists A prime of A. This is easy to prove. I'll leave it as exercise to show that given this hypothesis, you can find A prime in A such that A prime is of size linear in A, but since A is linear in N, so A prime is also linear in N, and every pair of vertices in A prime, so let me draw it, and for every pair in A prime, their common neighborhood is linear. They have linear number of common neighbors in B. This is an exercise. After proving this exercise, you will easily see that we are done, because why we are done? So this is true for every pair of vertices in A prime, okay? If A prime is a clique, we are done. We get linear size clique. Okay, if this is complete, we are done. Linear size. That means we can assume it's not complete, right? So if exists A prime not adjacent, so this is my A and A prime not adjacent. By the second property, I know their common neighbor is linear size. If this is a clique, we also done. Let me give you a name. Let's call this guy B prime. If B prime clique, we also done linear size. Otherwise, we get the induced C4 contradiction, right? Now the clique means there are two vertices not adjacent. Now you have two vertices not adjacent here, two vertices A prime not adjacent here. You have all edges in between. Induced C4. Good. That finishes the first case, that the density of A is more than 2/3. More than 1/2 is enough. So 2/3. Case 2. Density of A now is less than 1, less than 2/3. Okay, so here's the picture again. Density of A is less than 2/3. Now what I'm going to do is you clean the atypical vertices. Having wrong degree. So that just means you have some parts that we remove from A and B. The vertices here, so if the density between A, B is D, then the vertices here, the degree to the other side, it's out of the range D plus minus epsilon times B. Okay, for typical vertex, the degree should be D plus minus epsilon times B. So you get rid of those atypical ones, and such atypical vertices is a little o n. Okay, little o n, atypical ones. Good. Now all the remaining vertices, they are nice. Degree is as expected. Good. Now, since the vertices we clean is negligible, so the density in here is still at most 2/3 plus little o1. Okay, it's at most 0.7, say. So there must exist a vertex, its non-neighborhood is at least 1/3 of the remaining. Okay, so as dA is less than 2/3, there exists the vertex A in A, which is a typical vertex. There exists a vertex A in A, which is typical vertex. So what does it mean? That means that means know that the density in A, so we are in the second case where density of A is bounded away from 1, let's say at most 2/3. We clean the atypical vertices, so the remaining vertices, they have the correct degree to the right-hand side. So that means all these vertices, they have the right degree to the other side. They satisfy this blue thing, right? The degree to the right-hand side, that's called B prime, double prime, is at least D minus epsilon, which is at least epsilon proportion of the right-hand side. And we can also choose A so that since the density of A is strictly less than 1, so that its non-neighbors in A is linear in the order of A. Let me call it A double prime. So this inside A, let's call it A double prime, is at least, so this is 1/3, right? So 0.66, so let's say 1/4 of A, which is again bigger than epsilon B. What do I know then? Both of these is bigger than epsilon B. That means since AB is a regular pair, and each one of these subsets is at least epsilon fraction, so that means the number of edges, this implies A double prime and E double prime is at least D minus epsilon times A double prime, B double prime. Which, anyway, this is linear in N, so it's linear in N squared. Okay, that means what? That means we can find, by pigeonhole, a vertex A double prime in here, which is not adjacent to A. Exist A double prime in A double prime such that its degree to the other side is linear to B double prime, right? Such that degree of A double prime in B double prime is, by averaging, linear in N. Now we are done, because this part is common neighbor of A double prime and A. Either this is a clique, we have a large clique, or it's not a clique, non-adjacent pair in here form an induced C4. Then we get either induced C4 or linear size clique. We are done. That concludes the last application I want to mention. I wanted to mention how to prove for general T. Maybe I'll leave it as exercise to prove for general T. Basically, you use similar ideas here, but you have to iteratively either build a KT2 blow up, a KT2 induced copy, or you will find a linear size clique. You can use, for example, induction on T. The base case is T equal to 2, which I prove here. Give it a try. Any question? Okay. If there's no question, I would like to thank the people here who survived till the last lecture. I hope you find this helpful. The plan will be in the autumn. I hope to have the second part of this course, where here we laid out most of the basic things in extremal graph theory and extremal set theory. We're seeing regularity lemma. In the autumn, we will focus more on methods, different methods. So the material will be grouped into different methods with applications on some of the problems we've seen so far and some other new problems. Okay. If there's no question, then I will see you guys in the autumn. Stay tuned on our group homepage. If we have new course announced, we will make announcement there.